For this module, we're going to talk about what happens to an electric field when it comes upon a conductor. And then through that, we'll come up with a description for the boundary conditions in the case of electric fields and conductors. So let's just start out with an intuitive explanation. One of the key characteristics of a conductor is that the charge carriers are free. They can move about however they want. So what does that mean if it was in the presence of a uniform electric field? Over here we have a uniform electric field E, and then we have this conductor inside. What's going to end up happening is that the conductor is going to respond to this potential. So over here, it's going to sense some positive potential where all the negative charge carriers are going to be attracted to it. So you're going to have a bunch of negative charge carriers attracted to this surface here. And while there is remaining electric field, so let's just say there's still a little bit more positive electric field that's not completely countered by the electrons that are over here. What's going to happen? Well, more electrons are going to come, right? So more electrons are going to come until you have this negative rho s that happens to completely cancel out the electric field here. Similarly, you can view it from, since this positive negative is a little bit relative and arbitrary, you can also see the same thing happening over here, right? So the electric field here is going to attract a bunch of positive charges all the way until it cancels out whatever electric field it feels on the surface here. Because if there's any more that it feels that can attract more positive charges, then it will. Right? So in the end, you have the negative charge density rushing up in response to the electric field here, positive charge density rushing up in response to the electric field here. So then what is the electric field inside the conductor? 0. Right? Because everything outside of the conductor ends up getting canceled by these charge densities. Or let's just do another analogy that might help or hurt. If it hurts, then just completely ignore it. But let's just say that, so in the case of conductors, this is like if you have two dueling concerts. In an effort to make this timeless, I'm going to place a bet and say that Beyonce and Adele are giving a concert at the same time, and hopefully they will remain classic for the duration that people might be watching this video, so that it's not too dated. But let's just say that you have this conductor, and this is basically an open floor concert. So there's no seating, the fans can go wherever they want, and Beyonce is playing on one end of the hall, and Adele's playing on the other end. Well, what's going to happen is that, let's say Beyonce has this amount of star power, all the Beyonce fans and people that voted for Beyonce in that one year in the Grammys will rush over to Beyonce, and then all the ones that decided that they're really into Adele will rush over to the Adele side of the concert hall. Right? And basically, if you let the fans move however they want, which is the case of a conductor, you're going to end up with no fans in the middle. Right? There's nobody in the middle, because if there were any other Beyonce fans, they would run over here. If there were any Adele fans, they would run over here. And so you can think of over here, there's this translation where the electric field changes into a charge density. You can think of it as, in the case of this, Beyonce's star power ends up with this level of fan density that's over on this side, and similar with Adele. And then there's going to be no fans in the middle. And so what does that mean for the potential? Remember, the electric field is the equivalent of the slope, and then potential is the equivalent of the altitude. Right? So if we were to plot the potential of this conductor here, where this is the potential and then this is distance, outside of the conductor, you're going to have your constantly dropping electric field, because the electric field is constant. And then what is the slope in the conductor? 0, right? So the conductor will be held all at constant potential And then once you get to the other side, the electric field will then continue on the same slope as it had before. So one way to view this is that the electric field, or the slope, is going to be 0 inside, so it's going to be completely flat. The electric field outside will continue on either side of the conductor as if the conductor wasn't there. So it goes here, the conductor basically gives it a pause in the progress, and then once you get to the other side of the conductor, it just continues along its merry way. But in between, the potential is constant. And that matches how we believe conductors behave, right? Our understanding of how conductors behave. If you have a perfect conductor, and the voltage across that entire conductor is going to be the same everywhere. So let's use that and come up with an expression for the boundary condition, or what happens to the electric field when you're on either side of a conductor. I'm going to talk about this in the most general sense, and then we'll apply the situation of a conductor, namely that the electric field is inside, to get our final result. But we'll do this again with dielectrics, and you'll see that when you apply a dielectric condition where E is not necessarily equal to 0, the same process works. It's just what the assumption that you make of what happens inside the materials that are different. So let's start with a zoomed in look of what happens in a given boundary of two materials. So let's just say we're going to zoom into this interface over here. So this is the interface. Over here I have material 1, we'll just call this medium 1, and over here I have medium 2. And when I'm looking at the electric field, I can decompose the electric field into any two components that I want, right? In this case, because of the way the physics works, it makes sense to decompose the electric field into two components. The components that's normal to the surface, and the component that's parallel to the surface. So let's decompose that. We're going to have the tangential or parallel surface to look like that. We'll call that E1. And over here we'll have the same thing. This is going to be E2 tangential. And then on the other component that we'll have, we'll call the normal component. So this is the normal component in medium 1, and over here you have the normal component in medium 2. I'm not going to call these vectors because they are defined in relative direction to the surface, which let's just call this direction the normal direction. So this is the n vector. So E1 is going to be along the same line as n normal, as this n unit vector, and E1 is going to be perpendicular to that. Now in the case of the tangential fields, let me just start by talking about what we're going to do, and then we'll actually do it. But in the case of solving the tangential fields, we're going to use the fact that when we do a closed loop line integral over an infinitely small loop here, that the closed loop line integral is going to be 0, because that involves the tangential components, right? You have E1 tangential here, and you have E2 tangential here. For the normal component, we're going to actually use Gauss's law, where we are going to take the surface integral of these two regions, and that's gonna help us relate the normal components to each other. So this would be ds1, and this would be ds2. And if we use Gauss's law, again, let's just assume these portions are infinitely thin. That will allow us to relate the normal components to each other. So let's start by looking at the tangential components. I'll just use the green marker to emphasize that we're looking at this line integral and these tangential components. Let's see. Let's call this dl, and we're going to name these segments 1, 2, 3, and 4. As I said before, we're going to use the fact that the closed loop integral, E.dl, is going to be equal to 0. So for the loop here, let's just let's just define this as the x direction and this as the y direction. So the normal vector is going to be in the y direction. In the case of this loop here, we can rewrite this. If we assume that segment 2 and segment 4 is infinitely short, we can break this line integral down into E1 dl1 plus E2 tangential dl2 is going to be equal to 0, where dl1 in this case we can see is in the minus x hat direction and dl2 is in the plus x hat direction. So now let's call this an infinitely small segment. So 2 and 4 we're going to keep so short that it doesn't really matter, and we're going to call the length for segment 1 and segment 3 short length L. And so by short, I mean it's short enough that we can just call this L, and we can also pull the E field out, because the E field, it's going to be so infinitesimally short that the E field doesn't change. And so we can treat this as a constant and pull it out. So then we can then write that this integral is going to be equal to minus E1 times the length plus E2 times the length is going to be 0. The L's cancel out, and we find that E1 tangential is going to be E2 tangential. Which so this is kind of the main key take home is that the tangential component E1 and E2 are going to be equal across the conductor. So if you break the electric field down, or across these two regions. So in any two regions where you change the medium, the tangential fields are going to have to be the same on either side because of this conservation quality that you see here. Now another way that we like to write this in vector calculus, which also will allow us to extract the portion that's tangential, is that we can also say that the vector E1 minus E2, if we take the cross product with n, is going to be equal to 0. Now, in the case of a conductor, this is a general truth, no matter when we're going across these regions. Now, remember, what's the electric field inside a conductor that we talked about before? It's equal to 0, right? So that means that in the case of a conductor, so for a conductor, we have E1 is going to be equal to E2 is going to be equal to 0. So this also makes sense, right? If this is a perfect conductor, we're going to have no voltage drop in this direction, right? Therefore, no matter what happens outside, the basic result is that the tangential electric fields have to be 0 in the case of a perfect conductor. But in general, we can write that the tangential components on either side are going to be the same. Now let's take a look at the vertical component, or the normal component. So the component that is perpendicular to the boundary that we see here. As I mentioned before, in this case, we're going to use Gauss's law, which states that the closed surface integral of d dot ds is going to be equal to q. So let's just say we're going to look at this cylinder here, and we're again kind of similar to how we said 2 and 4 are going to be infinitely short. We're also going to make these two infinitely close together, and ds1 and ds2 are going to be such a small area that the electric field is going to be constant, so we can pull them out of the surface integral. And we're going to define ds1. Remember this, the surface integral, we usually assume outward direction to be positive. So ds1 is going to be in the y direction, and ds2 is going to be in the negative y direction as defined in our axes here. So now let's write out this integral. So the closed surface of d dot ds is going to be equal to the integral of d1 dot ds1 plus the integral of d2 dot ds2. And that whole thing is going to be equal to q. right, which is going to be equal to rho s times the surface area. So rho s times the surface area here is going to be the amount of charge that's built up. Now let's assume that this surface area is going to be equal to s. So this integral here is going to be the normal component times s, which is this surface area here. This integral is going to be equal to d2, but now remember this s is in the opposite direction, right? So because this ds2 is going to be in the opposite direction of ds1, so we have a negative s here, and that's going to be equal to rho s times s. All these surface areas cancel, and we're left with the fact that d1 minus d2 normal component is going to be equal to the surface charge density. Or another the vector calculus way of writing this is to say that d1 minus d2, so if we just take the whole vector, if we take the dot product with this normal vector, we end up with this relationship here. So the d1 minus d2 dot n is going to give you rho s. Now let's recall what goes on inside a conductor. What's the electric field and the electric flux density inside a conductor? 0, right? So we can also say that in the case of a conductor, d2 is equal to 0, therefore d1 dot n is going to give you the charge density. So similar to what we talked about over here, I gave you a general expression that is true across the different materials, which is that d1 minus d2 dot n, or the tangential or the normal components of d1 and d2, is going to be equal to the charge density on the surface. But in the case of conductors, we apply the fact that d2 is going to be 0, and we get to the description that d1 dot n, or the normal component of the electric flux density outside of the conductor at the surface, is going to be equal to the surface charge density. So one final thing that I like to point out before we wrap up is that since the tangential component is going to be equal to 0, anywhere where you have a conductor, it basically is an equipotential surface, right? So if you were to draw all the different potentials, in the end, whatever potential is on the surface of the conductor, that is going to be an equipotential line. So if you happen to be drawing the equivalent of what the altitude is or what the potential is in different areas, the conductor is going to be one of those equipotential lines, the surface of the conductor. And then on that surface of the conductor, the tangential component is going to be equal to 0, which means that if you take the gradient of the potential, all of that is going to end up being the normal component, because that's the only component that ends up being non-zero. So this is also, in terms of the bigger picture of the conductor, that's also something to keep in mind, especially this relationship here. So in summary, we talked about how a conductor is characterized by the fact that its charges have free reign and can move wherever they want. So in the presence of an electric field, wherever they want is to keep moving in response to the electric field until the electric field's gone. Therefore, the electric field inside a conductor is equal to 0. And using that, we also introduce the generic approach for how to find the boundary conditions, namely how to relate the tangential and the normal component of the electric field from one side to the other. In the case of the tangential component, we arrive at the fact that the tangential components have to be continuous across the boundary. And since in the case of a conductor, E2, if 2 is the conductor, E2 is equal to 0, so we have the fact that the tangential component of the electric field is going to be 0 across the entire conductor. Separately, when we can use Gauss's law to come up with the boundary condition for the normal component of the electric field from one material to the next, and through that, we find that the normal electric flux density is what we use to relate to 2. The electric flux density going from one side to the next is related by the charge density rho s. And when we apply the conductor situation, where we know that the electric field and electric flux density is 0, we arrive at the conclusion that the electric flux density, the normal component of the electric flux density, is going to be equal to the charge density at the conductor. And that's kind of how it cancels out the electric field and makes it 0 in medium 2. In the next discussion, we're going to go over a clever technique that we use to calculate the electrostatic fields in the presence of a conductor, but then we're going to do the same kind of analysis with dielectrics to round out our discussion with how dielectrics behave in an electric field.